All right, so I am back and I'm going to be discussing the topic that I didn't quite get a chance to finish up, which was global state. And I am streaming this now. I am recording it. I just adjusted the slides a little bit so that I can do this and trying to keep pushing the production values up a little bit. All right, so what we have is the completion of the lecture that I was doing earlier today. I'm going to back up just a little bit because I think it'll at least hold together a little more coherently here. So I'm going to start where I started discussing the Chandry-Lamport algorithm. And there were some really good questions about this conversation afterwards, and so I thought it's worth going back through these slides a little bit to try and capture these conversations. So there was a fair bit of discussion after the class about this consistency versus what we actually experienced. And and that's really important to understand, is that the state that we capture isn't necessarily the state that actually occurred. This is the mind-bending part. It is a potential set of states that could have occurred that would have led to the same result. It really is that equivalence, the isomorphism that we have, which is important for these. So let's go look at this in a little more detail. So I have all the possible runs, because remember, a run is just basically any sequence, any path through this corresponds to a potential run. And that means that we have a very large different set of combinations of events. However, as long as we run through that and we end up in the same exact state, it doesn't actually matter. So in this instance, I said, let's start with, let's take two different runs. And um, as long as we have different runs and they end in the same place, we're going to count them as being equivalent. And the reason for this is that it's good enough for us to preserve those causal relationships, and thus these are isomorphic. The way I intuit about this is, if I didn't see the details and they didn't affect the outcome, I don't care. It was my analogy from this morning, which was, if I walk from where I live to where I'm giving this presentation, or I travel from where I live to where I'm giving this presentation, it doesn't really matter whether I took the bus or I walked or I took a skateboard or I drove or I took an Uber or a helicopter. The net result and the thing that impacted your experience, in other words, it changed your state, was that I got there. You just care about the outcome. And this is going to help us think about the properties of these systems without worrying about all of the details. We're not going to micromanage the transaction. We're basically going to say, hey, results count. So I'm going to formalize this a little bit. We have these global state properties, and I spent a fair bit of time when I was writing these slides to make sure that I get uh, the nomenclature consistent. So hopefully I did. So we have S star. That is the recorded state. That's whatever we actually captured. And we're going to generalize this, of course, when we go to multiple processes, but we're going to start here with just one process, in other words. So we have some sequence, which I called S sub EQ. I suppose I could have done S sub SEQ, but whatever. We started at S sub I, we ended at S sub j, and for whatever reason, I'm going to say that's the true initial state. That is, in other words, an observed state. We could independently or externally validate that's where we started. And same thing with the true final state. And from my perspective, if I'm another process that relies on this, and I can see that that process went through those two states, I'm going to consider them to be true. So they are ground truth. These are to distinguish from probabilistic states. Well, I probably went through that route. So now we have this property. We know that S star is reachable from S sub I. That makes sense. And the reason I thought this was interesting is because the questions that came up after class related to, well, what happens if there's no channel back to the initiator of the snapshot request? Because as you recall, we were talking about the the markers, the marker that the initiator sends to the other parts of the system. And the question was, well, what happens if there's no channels back to the initiator? And I thought about that, and I realized that it's a good question. It's a really good question. And the observation there is that if you don't have any inputs, then you should never be an initiator. And that's not explicitly stated here. It's just one of those things that you realize as you start looking at it, saying it doesn't actually make sense. And my analogy there was, suppose that I am a service that just simply tells you what the current temperature is. So I just initiate that. I send out a message every so often. I don't get any messages from anyone else because my state doesn't depend on anyone else. So I actually don't care. And this was the interesting part, is that if I am sending messages but not receiving messages, either some other node in the system is using my state, using my information, and therefore they are recording it as part of their state, or no one's using it, in which case my absence or my presence makes no difference to the outcome of the system. So putting a process in there that doesn't actually save any state, that doesn't really participate and isn't relied upon by anyone else, is actually just easily excludable, trivially excludable. So we don't really need to consider that case. There was a more interesting case of what happens if I don't have a full connection, and I think that that was a good analogy, a good example, and we're kind of touching on this here, and that is if someone, and so then the example I gave was, suppose that I'm a timestamp service, and I just simply send out a timestamp beacon. The time is. Then if I combine that with the service that does the temperature. So the timestamp service sends out its message. The temperature service says, the last timestamp I saw was this. So the timestamp service talks to the temperature service. Now that becomes part of the state of the temperature service, because the temperature service says, my time state was this, my temperature state was this. And I'm going to send that to anybody who wants to know what the temperature is. So I have these channels that I can use to send to whatever the temperature is. It's like, okay, well, now the fact that nobody else depends on that timestamp is kind of immaterial. And furthermore, if I'm downstream from that and I'm getting the state from the temperature service, what I get is a tuple. I get a timestamp and a temperature. I can't tell whether those are two services or one service, and I don't actually care. As we start to generalize this, and we're going to see this in a broader form, as we start to generalize this, what you begin to realize is that either there is a path to get back to the original marker, or the component we're discussing is not dependent on, nothing else depends on that state. that's kind of the interesting observation there, is that if I don't tell anybody else about what my state is, so I only have inputs, I have no output channels, then I'm a sink, and my state doesn't matter to the outcome of the system. I'm just kind of more like a logging service where I'm sitting there monitoring silently the system as it's going by, but I'm not participating in it, and therefore I don't matter. This we can talk about that. We can look at that, and what ultimately we come to the realization of is we don't have to consider those cases. And it kind of feels like that's what we're doing here as well. So what we're saying is, look, we got all these potential states that we could go through. We have a path from state S sub I to state S star. And that means there is some computation, some series of steps. Now, so note, I just said reachable. Yes, the picture shows they are directly connected. I just said reachable in the text. So the picture is trying to help you get an intuition here, but in fact, the text is being very formal and very precise, which is S star is reachable from S sub I, which means there's a path from S sub I to S star. So either S sub I and S star are the same state. So this is kind of the trivial case where it all collapses down. Oh, well, we're talking about the same thing. And yes, of course, a particular state is reachable is self-reachable, I guess. Okay. So that feels like a very trivial instance. The more interesting case is what we can say then is, since it's reachable, S sub I is a previous state. And now again, that's S sub star is the reachable bit. And then we also can note that if there is another state, S sub j, and it is reachable from S star, then it's the same logic. Now we're just putting them both together, so you can see that if there's a path from S sub I to S star, and there's a path from S star to S sub j, then the same exact thing applies for the S star to S sub j. S star has to either be S sub j, or there has to be a path to it. And the cool thing here is that now we're going to actually see that S sub j is reachable from S sub I if both of those conditions are true. And that's going to allow us to establish this theorem, which is that the recorded state is always reachable from the starting state. And why? Well, how could I have recorded it if there wasn't a way to get from where I started to where I am now? So this feels almost tautological to me. It's like, okay, yes, I got here. I started here, and I got here, and therefore, gosh, there must be a path between these two. Okay. And then similarly, I can reason about the termination state and the recorded state, because this is just really an intuitive look of a picture that tries to capture what the formalism on the previous slide said, which is, okay, so if I can get from A to B, and I can get from A to C, because where I started and where I ended, obviously, there has to be a path, then the fact that there's an intermediate recorded state is great, and it doesn't change the fact that I can get from A to C still. So what is our global state? So we have these, or what is the stable property in a global state, rather? Sorry. So what we're going to do is we're going to define something as being stable if we reach a point where, for all of the states that are a successor of an initial state, so we have S, the initial state, we have S prime, which is a state that is reachable from S, is stable if that statement is true. Let me rephrase that, because I feel like I kind of walked through that the wrong way. So if we have a state S and a state S prime, where S prime is reachable for all of the states S prime, so then it is considered to be stable. And the examples here to try and make that a little more concrete is a deadlock. A deadlock might go through a series of states, A, B, C, but back to A, but back to B, back to C. So in other words, I'm now caught in essentially a loop. And I would consider that to be a stable state. Similarly, termination. Once I've terminated, I'm done. There's no successor state, or you could say that there is, um, the state is its own successor. Those are effectively the same thing, and those are considered to be stable. And the reason this is going to be important for us is because if we can recognize that something is stable, then we can reason about it better. The challenge here is how do we evaluate a property without knowing the system state? And this is again where this isomorphism is going to become powerful, because if I have multiple paths that go down different ways, reaching S star from S sub I and Sj, which is the terminal condition, from S star, then it doesn't really matter how I got there. In fact, all I care about is that I started at S sub I and I ended at S sub j. And the paths I got there don't really matter, because it's the same state. I don't care about what the intermediate things there were. Um, and so if we know that S star is stable, then we know that all of the states following it are stable. Similarly, we know that if S star is not stable, then we know that S sub I that follows and is reachable from S star is not stable. Okay, so stable, that one makes sense to me. Hopefully it does to you as well, which is everything that followed that has to be reachable, since that was the whole point of stable. It is said, every let's go look at that. Right, it's stable if for all states S prime is reachable from S. So here we are now. We've just, instead of using S prime and S, we now have S star and S sub j. If we know that S star is not stable, then we know that the preceding conditions are not stable. We can't actually comment on the following conditions, because there might be states that follow that are stable, but there might be some intervening states that are not stable. So we can't really say a whole lot about that. So what can we say about unstable? Unstable properties could be things that are transient in nature, such as buffer overflows. Oh, sorry, I don't have any space right now, but a few seconds later, I have plenty of space because I've dropped packets on the floor, or I've drained my buffers, or the state of the system has changed. Load spikes are a big cause of this kind of thing. So I have these buffers, the buffer fills up, I drop packets, I lose messages, and those are transient errors that fit into this unstable proposition. I mean, honestly, just data sources that are constantly changing. I mean, I was using the time, the weather, the temperature outside service. The temperature outside will change over time. It's not necessarily stable, and if that's an input for the state of the system, it may very well lead to instability, but it's not guaranteed. If all I'm doing is just simply recording what the temperature was and not actually acting on it, then it's not going to affect the operations of another process. Um, Race conditions are a really good example of instability, because they are a manifestation of non-determinism. Again, effectively, anything that's non-deterministic would create instability in the system. Race conditions are transient errors. They happen occasionally. They don't happen all the time. So you might perform the same operation multiple times, and sometimes it works, and sometimes it doesn't. Indeed, one of the frustrating things about working with race conditions in the real world is that real world race conditions don't happen very often. They're often very difficult to reproduce, and typically they only happen in high stress situations because they are low probability events. So if something is unstable, there's no guarantee that S star even actually happened. Can we do anything with distributed snapshots here? So we can say a little something. If y is a stable property, then if y is in state S is true, we know it's true. It doesn't make any difference how we got there. But if y is not stable, then if y sub s is true, but we don't know if, so we can't say anything really there. It could be true or it could be false. Not stable just simply means we don't know. For example, we don't know if it's in a consistent state at that point, so we can't rely upon that. When we're reasoning about this, what we're going to really look for is stable properties, because stable properties are going to allow us to reach conclusions. But knowing when things are stable, or knowing when things are not stable, doesn't mean we can't figure it out in a different way. And indeed, I think that the point here is, think of this as an open problem. What could we do differently that might allow us to understand the properties of this better, and maybe we can do better with other techniques. So to summarize what we talked about, it's hard to detect global state in a distributed system. I talked a lot about why we don't have a global observer normally. If we posit a global observer, none of these problems occur. We can actually eliminate that. If we force our systems to be so deterministic that we're going to ignore the cost of sending messages and whatnot, then we end up with a not a very usable system, but we can get rid of these problems. So the reason we spend a lot of time talking about these problems is because in order for us to do something about them, we actually need to understand that we can still learn things just from uh, taking the distributed snapshots. We are going to build on this more. We are going to talk about the use of these isomorphic observations, because it's going to become very important as we begin to reason about things. The other example I used after class today when people were asking about it, as I said, this is kind of like modularization, where we ignore what happens inside of the module because we know what its inputs and its outputs are. And this is just a manifestation of that in terms of distributed systems. And with that, um, this is a great time to ask questions, since this is, of course, being streamed and recorded. I expect that the questions will come either on Piazza or on Discord or at office hours or at the next class. So I'll see you next class.